Hi everybody. Well, after taking a lot of pictures, I got the capacitor filter boards apart. You can see there's a lot more going on this board than what it looks like on this side. You can see, and we're going to have to rebuild or test all that. Okay, I'm testing out all the components on this board. And this is the protect circuit. This is what drives the protect relay. And this is what monitors your signal for offset and so forth. And one thing to note is at the input of that circuit, you have this capacitor. And you see this on a lot of protect circuits. And in most cases, they're a little bit naughty and they put a polarized capacitor in there, even though you have an AC signal going in there that changes polarity. And the current is so low that usually you can get away with it. But on this one, they actually put a proper non-polarized capacitor in there, or a bipolar capacitor. So I had to replace that. Luckily, I had one of those in stock. So after a little bit of work, the board's cleaned up, and it's better than it was, at least. And all I did was I took some of this copper foil, and you can buy this stuff at the craft stores and everything. Make sure it's pure copper and not aluminum with coating on it. But you can buy this pure copper foil, and it's not super expensive if you buy it in the craft store. It comes in rolls. And one roll will last a really long time because you just use little pieces like this of it. And I cleaned off those terminals, and I scraped off some of the paint on the board. And I just soldered these on there to kind of make patches to fix the tracks, because we're going to re-drill these. And the reason we're going to do that is that I need to use a different type of capacitor. The capacitors available, and you could probably find almost drop-in replacement sized ones if you wanted to shop around enough. But from what was in stock and you know, where I order things, in this case was DigiKey this time, they only had two different caps that would fit. One had the correct case size, but they had screw terminals, which I didn't want to use those, even though we could have drilled these out bigger and used them. The other ones are smaller and have a little bit different pin spacing, so I ended up going with them because of the specification. I'll show you here what they look like. So here's the original ones. You can see the size with, you know, comparison to the board, how they go in. And here's the new ones. Oh, little baby capacitors, aren't they cute? But all kidding aside, they're a lot smaller, and these are 12,000 microfarads at 63 volts. These ones are 13,000, which, you know, I did a video on this. Increasing that value has to be a whole lot before it makes any difference. So really, it's, for all intents and purposes, it's the same. They're both plus and minus 20%. So, but the difference is they are a little bit smaller diameter, and they are much shorter, as you can see. And I think we're going to be really close to having those clamps be able to fit, because if you look, these clamps really stand off quite a bit. So even if we clamp it clear at the very top like that, I don't know, that might be enough. I think that's going to be enough. But as you can see, they're barely going to get to the top here. And since they have a different size, and I've done this trick before, I'm just going to use a piece of this weather stripping gasket. It's kind of a foam rubber stuff, and I'm just going to line just one side of it, you know, like this, like a U shape, and then it'll clamp against this plastic, and that'll fit right in there, and that'll hold it very securely. Now the other thing is, these are snap-in type capacitors, and these ones are tab mount capacitors. So the spacing is different. So the holes are going to need to be a wee little bit wider, and they're much tinier. You see how small those pins are. But to help with that, they give you 2 holder pins, and these are dummy pins. They are not electrically connected to anything. They're not connected to the case, they're not connected to any terminal or each other. They're just strictly there for structural stability. So we're going to have to drill those out, and I'll show you how I do that here in a minute. Now on the top side, you can see where the new capacitors are going to go, and just so I don't get confused, I marked the positive and negative terminals of each capacitor, and you see how those are connected together. So if you go from here to here, if you measure underneath, like from test point 24 to 28, you will actually read the full voltage, the positive and negative differential. So if it's 57 plus and minus 57 volts, it's actually going to be 114 volts DC across here. And we're going to find out why I say that here later on in the video. But first thing we need to do is we need to get these drilled very accurately. And in order to do that, what I did was, since these are sharp and pointy, I just took a piece of, cue card stock, and I poked these down through there and then cut the circle out. And this gives me a template to line up and to mount this. So what I'm going to do is I'm going to line these holes up with this, and then I'm going to figure out where we need to put it, and then we're going to drill those 4 holes, and we're going to do the same on this side, and then we can get these mounted up. Okay, I don't have the microphone on, but it's right next to me here. So I'm going to put I did this template already on this side. So now we're going to go over to here, and I have it flipped the other way around. And I'm just using a pin vise with a little tiny drill bit to begin with, just to start a pilot hole. And that just gives us a little dimple to work off of. Just like that. And then we can follow up with an actual drill and carefully drill it out. And you can see the little 4 holes there. And I'll get those popped through with a drill, and we'll be right back. Okay, and after drilling them out, it looks like that on this side, and then on this side I just scraped off some of the circuit board paint on this side, and to allow to solder those tabs down. And we'll clean that up after we're done getting this all assembled. And hopefully, if we got this right, everything should fit right in here. Let's see. Okay, pretty close. There we go. And then we're just gonna, and then this will just push in, and actually I have these holes just a little bit bigger than these pins, so I'll press fit those in, and like so. Okay, there's what it looks like top side compared to the old capacitors that have not been removed yet. And here's what it looks like on the underside. And I think that's going to work out pretty good. Okay, the power supply and filter boards are put back together. And those are really good capacitors, by the way. One of the other things is these caps were rated at 15,000 hours at 85C. They were also high ripple current. They're pretty low ESR, and they do have some dielectric absorption to them, because just sitting there, they'll pick up a little bit of a charge over time. It takes a while, but there is a little bit of that going on. But these are really good caps, and I think they're going to last pretty much a lifetime. Unfortunately, the wires going over here had been cut so many times, because this is the side that had the most work done on it, as you can see, and I had to patch it. So I had to put some new wires in, and what I did was, they're the same gauge, but if you notice, the outside of the wire is a bit thinner, but the conductors are exactly the same. These are 20 gauge solid copper tinned wire, and the main difference is these ones are rated at 600 volt insulation, and I don't know if you could see it on there or not. Where does it say? Somewhere it should say 600 volts, but these are 600 volt, and these ones are 300 volt insulation, which is perfectly fine for this. If I was working on tube gear with high voltages, that might be a little scary, but this is very good wire, and it's exactly the same conductor, so in diameter, so we should be good. All wired up. Now the only thing we have to do is we're going to install the heatsink and the power module on this other side and get it put together over here, and then we'll be ready to put the transformers in, and then I'll probably clean up this regulated power supply board before we power it up. Okay, now that I have that just kind of roughly held in place, that gives us an idea of where we need to be. I'm just going to take a Sharpie marker, just a fine point one, and I'm just going to put a mark on the pin here, right where it's flush with the top. And I'm going to do both sides here, and I have to move this around where I can get to it around the camera. And then all I'm going to do is I'm going to remove everything, and I'm going to solder those pins in right there, because really what you want is you want this to be, you don't want any kind of stress to be on this board when you put this in, because that's just going to push those pads out. And remember, the pads on these old boards are not real well fused onto the board itself. So if you put this thing up too high or down too low, it's going to really pull on things, and it's not going to fit correctly. So you just want to make sure you do that. You don't want to put any strain on this thing. Okay, to put these wires back on, I'm just going to use one of these wire wrap tools. And you can see there's a hole in the middle, and then there's a smaller one along the side. And what you do is you put the wire along the side, like that. And then you place it over the pin that you want to wrap onto. Hold it. And it wraps it on there. Now I'm going to touch these with a little drop of solder on them because, again, we're not going on to brand new shiny pins. So I want to make sure I get a very good connection. But this puts a neat mechanical connection on there as well. So let me finish putting those on, and then I'll tack these on, and this thing will be ready to put together. So first thing I'm going to do is I'm just going to loosely mount this board in here, like so. Okay. And that just kind of gets things where you want them. And what we're going to do is I'm going to get everything started. There's a flat washer, a lock washer, and a nut that goes on. Which is very difficult. I probably could use a pair of pliers or something and start it, but I'm just going to fiddle around here so all of you can yell at the computer screen that I'm not doing it right. There's some easier way to do it, which there probably is. Okay, and I am missing one washer, and there was a washer missing from this kit when I got it. Okay, we have a replacement flat washer. Yeah, that was kind of strange. It's just everything was in there except that one flat washer. I only got 3 of them in the kit instead of 4. Probably just an error on their part when they were boxing it up. But I know nothing about this Pyramid Audio company. I've read, some things. I've seen a few blurbs on them, but I really don't know much about these kits other than They look pretty solid. And once again, I am not, this is not a paid endorsement or anything. This is me learning too. I saw them, and it seemed to be a good alternative to trying to find those really expensive, TA100WA modules, because they're overpriced for what they are. And it's supply and demand. They made a lot of these amps, so there's still a lot of them probably out there in the wild, and those modules fail just like transistors can fail. The only difference is finding a transistor sometimes can be easier than trying to find those modules. Now what I do, just to finish it off, is I just put a drop of thread locker right on the end of the screw and on the washer, and it'll soak in there a little bit. I could put the thread locker on before that, but then it gets all over your fingers, and I didn't want to do that. So now the only thing really that we haven't serviced is this power supply here, and I'm going to go ahead and do that as well, because with these transformers in the way, it just makes it all that much harder to get to everything. I did get a new relay. I'm just going to shotgun it and replace it. These usually are going to be tarnished by this time, and yes, I could take it apart and clean it, but we'll look at it maybe if I get a chance, but my guess is that it's going to be pretty pitted up because how much work has been done on this. I think this thing, had some high current through it. But anyway, we're going to replace it with a Omron MY4-02 24V DC. So there it is. And again, check out the last video I did on the Pioneer SX 1250, and we talk a little bit about how these contacts are definitely not rated for the job that they're doing, but unfortunately this is what they've always used, and there's really no accommodation for a larger relay. And honestly, once the relay is closed and the contacts are closed up, you're good. Where you have the problem is if you have the volume turned all the way up, way up loud on the amplifier, and then this clicks in onto the speaker load, and that's what arcs these up and trashes them. So, all right, let's get working. All right, I've replaced the capacitors and the relay on this board, and I noticed from that glue that was used to glue down the old capacitors, the legs on these two diodes are just corroded really bad. So I'm just going to replace these diodes because of that corrosion, because sometimes that'll creep up into the diode and trash it. Okay, I have the board rebuilt, the little power supply, replaced the few capacitors that was on there, and you can see here and here the new diodes and the diodes on the other side. And I'll tell you what, that glue was miserable to clean off. I tried alcohol and it wouldn't loosen it up, and I finally ended up having to use acetone, and even that was hard to get it. It was really hard getting that glue off. I tried heating it, didn't want to put too much heat on it, but it really took some elbow grease, but I got it off and it's all clean now. Okay, let's get the second of our transformers in here, and they cleaned up really nice. I was surprised how well these cleaned up. See if I can do this without scratching it all up now, huh? That's the next thing. Okay. Probably should have had these fasteners ready before I started this, huh? All right. Okay, 3 more to go. It's actually starting to look like an amp again, isn't it? Get these last two in, and then we'll kind of figure out how we're going to get this wiring back in. Well, I went to flip this back over like this and realized that all of a sudden it got a lot heavier. It's amazing how much gravity that these two transformers add to it. So now what we're going to do is I'm going to get these wires routed in here, get them sorted out. Of course, the red, if we look here at our schematic, at the transformer down here, the red and white wires are your primary winding, and then the orange are the 43 volt, with respect to the black grounds, and then you have the pink and violet wires is your 30 volt windings. So we're going to get those connected up, and so they pretty much all, well, most of them go over this direction. I do think the orange wires, the orange wires go over here to our main power supply. The white and red go over here, and the pink, of course, and purple go over here as well. So let me get those wired up, and I'll show you the final results. Okay, we are going to make a little modification to this circuit. If you remember, we put 4 new capacitors in there, and it totals up to 52,000 microfarads at 63 volts. And of course, this, the main power supply for the amplifiers is plus and minus 57 volts. Bottom line is the inrush current on that capacitor bank is very substantial, and it's very hard on the power switch. And it's also a big shock on the transformer when you first turn it on. So what we're going to do is we're going to add a soft start circuit. And the way we're going to do it is we're going to put that soft start circuit right in line with the AC mains. So if you look, you have your power cord coming in right here, goes through the switch, and then it goes out to these 2 fuses right here. So what we're going to do is we're going to take the lead that's on this switch, and we're going to pass it through a little soft start circuit. Now the circuit we're going to build is a little board that I designed a while back, and I used this on another project earlier, and it just consists of 3 components and a circuit board. It's very simple, but it's very effective. And by the way, this is a legit circuit that is used in a lot of other high-end audio equipment. So it's just a little bit of a modification from what you normally would see. Let me draw out a schematic of what this is. Okay, so if this is your incoming line, here's your power switch, and this is what we have. We have an inrush current limiter, and right now I'm just using a CL40, which starts out at room temperature at around 5 ohms, and then it drops substantially as it heats up. And what that's going to do is that 5 ohm resistor, it's going to act like a resistor. It's going to limit the current on the primary of our power transformers. So I'm just showing one transformer, but if you look here, it's driving both of them. So that's a lot of inrush current. And that inrush current can be magnitudes of, hundreds of amps for a split second. That's really hard on a power switch and on your incoming line and everything when you first turn it on. So that might be one of the reasons that the fuses, the thermal fuses in those transformers fail, because of that huge inrush current. I don't really know. Again, thermal fuses are kind of their own thing. They don't work like a normal filament fuse, but nevertheless, overloading them can possibly cause them to pop, especially if they've been thermal cycled and things and they're weak already. But anyway, this is just going to allow the capacitor bank to charge up slowly because you're limiting the current. And then if you look, here's the coil to this relay. And the coil goes through a 10K dropping resistor, and this is determined, you're going to use a little bit of Ohm's law to determine how much current is supposed to be flowing and what kind of voltage drop you need to get the proper voltage and current across this relay coil. This relay coil is about 2.8, this one exactly, which is a Omron G5Q 1A4 DC22. It's actually a 24 volt relay, and it has about a 2.8K coil resistance. And so this resistor is going to be determined based on, we want the difference between the 24 volts at the current that should be flowing through here, which I think is somewhere around 8 milliamps is what this thing draws. And that's going to be based on the fully charged B plus voltage of your cap bank. Now you can put this across one capacitor bank or both. I'm doing both. And so where this is connecting, these two wires, I'm picking one of the channels, like for instance this one here, and I am actually going from one side of the capacitor's bank to the other, from the positive side to the negative side. And what that's going to do, and you can see how right here, the positive side of this bank, which is going to be your negative supply, ties into the negative side of this bank, which is your positive supply. See? And your plus B and minus B. I'm literally going from here to here, from my B plus to B minus, which is going to be your B voltages added together. So if you have a plus and minus 57 volts, that's going to be a net total of 114 volts DC. So if you take that 114 volts and you divide it by the 10K, you'll get the current that's flowing, and you'll be able to determine the voltage drop, and everything kind of falls into place. And these relay coils are pretty forgiving. You can go over a wee little bit, not much, and you can go under quite a bit. So what's going to happen is, as this voltage, you know, this thing's going to be limiting the current, and it's also going to be heating up. As the capacitor bank charges, that voltage drop across this whole mess here is going to increase. You're going to have higher and higher voltage across here until finally you get enough voltage to pull in this coil. Once this pulls in, this is going to short out this inrush current limiter and allow full power to the transformer. Now some of you might say, why do you need to do that? Because when this heats up, it goes down to, you know, like 1/10 of an ohm or something. Well, the problem is the way that it goes to that 1/10 of an ohm is it gets really, really hot. And I don't want a little mini space heater inside my transistor amplifier. So I want it to come out of the circuit. The other thing is, when these things sit there and run hot, hot, hot for a long time, they eventually will fail and wear out. We use these a lot for light bulb starter limiters, because if you put an inrush current limiter in series, for instance, with a 24 volt, you know, halogen 150 watt lamp, the filament's going to last a lot longer when you soft start it this way. And we just leave this in circuit with the light bulb, and it gets really hot from the light being on, drawing current, and these eventually will crack open. So I don't want that to happen. So this is only going to be in the circuit long enough to limit the current to the capacitor bank, and then this is going to short out. You know, this is going to pull in and short this out and be like a straight piece of wire. As the capacitor bank discharges when the thing shuts down, this will actually help discharge, well, this will actually help discharge the cap bank, and as it drops down below the holding voltage of this coil, this will pop back open and reset itself for the next time you turn it on. The neat thing is, if you turn this off and right back on and the cap bank is already partially charged, this will be already in, because it's not needed because the caps are already pre-charged past their really inrush current area. So it's a cool circuit that's really simple, and I just designed this little board, and if you look, there's actually a pad under here, a copper pad and everything. I actually originally designed it that you can put those little TO220 cased high wattage, low ohms resistors, and it'll fit directly in there. So I could use a resistor or this ICL. So it's kind of versatile. So anyway, there it is. There's 4 wire connections, your AC in and AC out, and then your DC rail, which is here. That's it. So let's wire it up, and where I'm going to put it is this bracket on the side here. I'm just going to mount it right here. That'll be out of the way of everything, and that'll be just right. Okay, well, there it is. And I have a nice new power cord on it. Have everything wired. If you look up here, you can see there's the soft start board right there. And we're monitoring our power rails right here. And then we have the nice thick wire going down to the power. And this should be it. So hopefully this will work. So I have it set, have the dim bulb set, and I have it on the smallest bulb. And I'm going to just plug this in. I checked it. Everything appears to be okay, but you never know. I had this thing way torn apart, and I had a lot of things on it. Okay, power switch is off. See if I can get this whole thing in here. I'll turn this on, and let's see if this thing will work. Well, our capacitors are charging. This is good. I heard one click. And I do not have a protect relay yet, which might be a bad thing. But it could be that I just have such a low voltage right now. So let's see what we have here. Can you see? There's too much glare. There we go. Okay, so let's start with the ground. Let's go to this rail. I have minus 38, plus 38, minus 38 there, plus 38 there, or 37.8 if you want to be exact. So all of our voltages are there. I don't know if I have my low voltage supplies yet, but I'll have to look on the schematic. But so far, this is a good thing. Obviously, we're not drawing very heavy current because this bulb has really dimmed down. And this is, again, this is only like a 40-watt bulb. So we're really, really limiting this. But the nice thing is we heard the soft start relay come in, or at least I heard it as it charged up, and it took it a long time to do that. And everything appears to be okay. What I don't know is what kind of DC bias we have, but we can look on the, or I'm sorry, not the bias, but if there's any offset. And there might be because the voltage is so low on here, but let's see. Here's our first speaker terminal. Oh yeah, that's pretty bad there. And that one's not bad. So I have about minus 1.4 volts on that one. And I got the full DC rail on this one. So something is still not right. Okay, it really helps if you get the wires on the right way. And I can tell you now from experience that if you swap the shield and the signal wires on the input terminals of the power amp board, you will get excessive DC offset. So now that we have this switched around the right way, let's turn this back on. And of course the bulb is limiting the current. Oop, and that just came in. And you can see now there is no DC voltage there, which is a good thing. And if we go to our speaker terminal, it's about minus 1.4 volts there. And the speaker terminal here is about minus 1.35. And that is just because I have those 10 turn pots in there. And if you remember, I just kind of roughed in the DC offset settings on the bench. So what we're going to do now is I'm going to dial that in on both of those and then increase to a bigger current limiting bulb to allow more DC rail to get in there. And then I'll fine tune it and we'll just walk our way up and hopefully the protect relay will pull in. Okay, I have the amp turned around where we can get to it, and I have the one probe connected to the output of the amplifier and the other one to ground, and we're measuring our DC balance or DC offset, however you want to word it. And I'm going to rotate this the wrong way. And like I said, we're going to just have to, we'll probably have to trim this up too. Let's see here. Like I said, I'll have to touch it up. There we go. Bringing it right down. Perfect. Now I'm going to move over to the other channel and do the same thing. Okay, I think I have everything in shot here. So let's go up here. Let's see if I can get on this without getting in your way. Here we go. Let's see if I can turn it the wrong way again, and I did. Let's see if this end will go on here. Yeah, that's much better. If you don't get the right tweaker for the right trim pot, it won't fit on this side. Did I go right through it? I did. I was not paying attention. Okay. This one's a little more fidgety. Got to creep up on it. There we go. Nice. And looking at our regulated supply that we rebuilt, we have our plus 30, which is 30.5, which I'd say is pretty good. And our minus 30 is minus 29.2. So very good. So everything's good. I think we're all right. Okay, signal generator is connected into the auxiliary jacks, and I have 400 hertz, and I have both of the channels of the scope connected to the right and left channel outputs. And let's turn this up and see what happens. And nothing happens. Look at that. Oh boy. Look at that. Not good. Well, first of all, let's turn my other channel on. There we go. Sorry. And you can see how jumpy everything is. This pot's bad. Okay, the easiest way to deal with this, I think, is just to remove the whole pot assembly off of the board. And it's pretty easy if you have either desoldering wick or one of these desoldering stations. It's not a bad deal. Oh boy. So you can see inside here that this definitely needs cleaned. Okay. $24K there, and that's the loudness tap. 87.4K, that's a weird value. Let's see what this side looks like. Same thing. So that's obviously what it needs, what it's supposed to be. Okay, here is the center, the wiper ring, and you can see the way this works is this outside tab right here, this is what goes on the center ring, and then these wipers actually make contact with the resistor material. So this is your actual center tap. So we should have a good signal, or if we should have basically a short from here to anywhere on this ring. And we pretty much do. So the first thing I'm going to start with is just some plain old isopropyl alcohol, just anhydrous isopropyl. And we're going to see if we can just clean off some of this crud. Because this doesn't look like tarnish. This looks more like something was sprayed on here or something, I don't know. Or just maybe just general crud. I don't want to put anything abrasive on here right now. I just want to clean it up and see where we are. There we go. And it appears to be cleaning up. Alright, so now that we have a better idea of what this looks like, I'm going to take one of these little fiberglass brushes. And this is soft fiberglass. This is not, again, not real harsh. And I'm just going to go right around this ring and clean it. Okay, just like that. Anywhere that's like a contact material, I'm just going to clean with this. Okay, notice I'm not going to go onto the carbon with it, because I don't want to take any of that carbon off, because that's going to change the resistance of it. I'm just going on the metal contact surfaces. You can see right in here where those are. So a true stepped attenuator has real actual switches. This has detents that act as switches, and that outer wiper makes contact with these, and this is what picks off the different resistances for the volume control. Let's see if we still have a good measurement here. If we go from here to here, we have our 87, and you're not seeing anything because I'm off camera. Here we go. So if I go from here to here, 87K. Now if I go from here to the wiper, much better. And then from either end, there's 63K there, 24K there, and I think that's good. Now let's put a little bit of treatment on it. Okay, for the metal contact surface in the middle, I'm just going to put a drop of this red deoxit. This works really well for the metal parts. And I'm just going to rub that in there, like so. Okay, just like that. Or you could just use green deoxit on the entire thing if you want. And then I'm just going to take a drop of this and just kind of put a couple drops around here. And then I'm going to work that in with one of these, just to get a little bit of treatment on there so that corrosion doesn't come back so quickly. That's all. And I'm going to even put it on this whole thing, and hopefully that'll keep that corrosion from coming back anytime soon. Here, I just realized the camera wasn't turned back on. So I'm going to put this like so. And then I'm going to hold this together and find something that'll go in here to bend these tabs over, like so. And I'll just do diagonally here to get them in place, just like that. And I'll do these other two. You can't really bend these too many times or they'll snap off, but you can do it once or twice and you'll be all right. Okay, now when I do that, I'm going to just rotate this, and yeah, that's moving very nicely. Then this one is going to go this direction, like so. No, it doesn't. Tony. This has to go on first. Why didn't you guys tell me that? It's your job to keep me in line here. Okay. I was just testing you all out. That's what I was doing. Yeah, that's it. And before I do anything else, I'm going to put this little snappy ring thing on here, like so. And then I'm going to push it down on. It's kind of like a wavy washer. It wasn't super tight when I put it on there. I think it's just, this is what actually holds everything together. And this goes like this. And then we bend these over. And hopefully everything will be functional. Let's see here. I could probably use pliers now to bend these over. And let's measure this and see if we have success. Okay. Oh yeah. Each click. Perfect. All right, let's go to the other side. And I bet you if we measured each of these resistances and we did the math, we would see that it'll be a logarithmic taper. That'd be an interesting thing to do one day, huh? Okay, these are all good now, and the wiper's working much better now. Okay. Okay, after cleaning the potentiometer and reassembling it, let's see what we have. And I'm on 20 volts per division, so. And there's your clipping, and I have both channels superimposed over top of one another, you can see. So they're perfectly tracking. Here's our balance control. Works. I think we fixed it. Okay, before we button this up and test it, we want to address the panel lamp, the 2-meter lamps. And there's 2 of them right here, and I can probably zoom you in a little more. And you can see they're right here, and they're in series. Pin 13 really is just a binding post for the 2 lights. And these 2 incandescent lights, they're 8 volt, 150 milliamp lights. And they're in series, so basically you're looking at 16 volts at 150 milliamps is what we want across here. And what they do is they come off of these 2 windings here of this transformer. So you see the pink and the purple windings. And they go down here where they go into the power supply and everything. But we can trace that because where it goes, I don't know if I can get this whole thing in here. So the first one is pin 16 on this board, and it's this brown wire, and it snakes its way around, and it goes right up to here. And then the other one is this green wire, and it goes and snakes its way around and goes right up here and right next to it. So it's right on that one winding. And in order to get that 16 volts and get the current limiting that we need and so forth, they are using 2 dropping resistors, and they're both 56 ohms at 2 watts. So you have, basically, since they're in series, you have 112 ohms at 2 watts. And if I measure from pin 16 to pin 12, there's 16, there's 12, indeed, I have about 112 ohms. I don't know if you can see, well, of course you can't see it. Let's get this a little more in view here. And you can see if I go 16 to 12, there's your 112 ohms. So the dropping resistor is good. Now, there's two options here. If we go with the first option, which is just replacing the incandescent bulbs, that'd be pretty easy, but these aren't bulbs that I have in stock. I'm sure I can order them. I'm sure I can make something up. But if you look at them over here, who thought we'd be talking about a light bulb for this long? They're blue, which is nice, but if you take them apart, you can see they're just soldered on there. And I don't think I have an 8-volt, 150 milliamp bulb like this. So what I'm going to opt to do is I'm going to replace this with an LED, but that is going to have a different, first of all, it's AC voltage. So we're going to have to take that AC voltage and convert it to DC. And then second of all, we're going to have to take that 16 volts and drop it to whatever the diodes or the LEDs are going to draw. So we're going to kind of have to modify this a little bit, but I want to do it in such a way that I'm not modifying the board. I want something modular that can be a part of the LED lights, so if they want to return it to the standard 8-volt incandescent, we can do that very easily. So it has to be something that plugs right in place of the old bulb and works. Okay, so here's what I decided. So we have two lights that are like this. These are just these rubber, and they're actually still like brand new. They're in great shape. And I took a blue LED like this, and I slid some sleeving over the leads and then put it right in just like that. And now we have a 30-volt AC power supply driving this. So if you take 30 volts AC times 1.414, if you full wave rectify it, you're going to have about 42 and a half volts DC. And so we're going to, and since it's such low current, it's probably going to be pretty close to that 40 volt range somewhere. And these little LEDs have about a 2.7 volt drop on them, 2.8 volts, something like that. So if I put two of these in series, so I put them in here like this, I put them in series, that's going to be about a 5.4, 5.6 volt drop. And these LEDs draw about 3 milliamps of current. So if you do the math to drop that 40 volts or 42 volts down into that range we need, we're going to need about a 12.2 to 12.5 K dropping resistor. So here's what I came up with. I made this little power supply board. It's just a full wave bridge rectifier. Takes the 30 volts, rectifies it, little smoothing cap, and then to spread the heat a little bit, even though there's not hardly any heat at all, it's maybe 1/10 of a watt, if that. I have two resistors. I have a, what did I do, a 5.6K and a 6.8K, I think. Yeah, 6.8K and a 5.6K. And coming out of that, this goes to the two LEDs in series, and this goes to the 30 volts, and I have the same colored wires to go around on the back of the board. Drilled a little hole in it, and it just so happens that right next to where they're going to be, there's this heat sink has the mounting flange that's with an unused hole right there. So I'm just going to screw that right onto there. And it's right there. And we can reverse this, just take that out, put the incandescent bulbs back in. I'm not doing any modification to this rubber mounting stopper. So we can take this out and put an incandescent back in. So if somebody ever wants to return this to original, it would be very easy to do. Okay, it's all wired up. And yes, there is heat shrink on these. I've had people comment, why don't you put heat shrink? There is. It's clear heat shrink. And I really like it because it works better than some of the traditional black heat shrink or colored tubing, because it's a lot more flexible, a lot harder to tear. It's really good quality heat shrink. So let's turn this on and see if it works. And there it is. And you can see it's not overly bright, and that's what we want. So let's get these mounted inside there and see what they look like on the meters. Okay, let's turn off the lights and see if they glow. And here we go. And that's exactly what I wanted. Perfect. Turn it off. And there's the finished product. I think it looks pretty good. And again, you can adjust the values of those two resistors according to your liking to make it, you could dim it down, or you could go a little bit brighter, or you could even substitute those LEDs for high brightness ones that will be brighter, but I can't imagine why you would ever want it to be bright like that. Okay, there's the final shot of the bottom of the unit before we put it back together. And final shot of the front, or the top I should say. And I think this should be good for many years to come. Now let's hook it up and see what kind of performance we get. Don't want to leave that on too long. Well, there it is all together. And I think I'm going to get this one posted up on YouTube and get it edited, and then I'll do a follow-up video once I get the covers cleaned up and everything, and we'll do the actual testing of the performance of the amplifier, because I think that'll take too long, and this video is probably already too long and it's going to take me forever to edit. So it's done. It sounds fantastic. I was really surprised. What I like about this amp is at very, very low volumes, it has a very clear sound. You don't have to crank the volume up to get a very clear, balanced sound. Not every amplifier always does that. This one does a very good job of it. So this is a really good amp. And I'm very pleased with the way it turned out, and I'm really kind of actually excited to find out how it performs with the tests. So that'll be for the next and last part in this series. Until then, I wish you all peace, joy, happiness, and good health in your lives. And, well, I have some other things I really need to get done here before long, so I'm going to hurry up to finish this and get it off the bench. So take care, everybody, and stay well. Bye-bye.